Welcome to Chemistry 1151, Survey of Inorganic Chemistry. My name is Dr. John Schwinn and I will be your instructor for this course. This is a 15-week course that meets over the Angel website, so you'll find many of the PowerPoint presentations and additional information through the Angel website. I will try to conduct office hours before laboratory meetings on Monday from approximately 4:30 to 5:30. If that changes, I will let you know. My email address is jschwind@southeasterntech.edu. The required text for this course is General Organic and Biological Chemistry, Structures of Life. Should be the 4th edition, written by Karen Timberlake. You will be required to have a scientific calculator for this course in order to complete the calculations in the homeworks and the exams. This course is set up to be an introduction to many of the basic chemical principles and concepts in order to explain the behavior of matter. The topics will include measurement in units, structures of matter, chemical bonding, chemical reactions, gas laws, liquid and mixtures, acids and bases, salts and buffers, and nuclear chemistry. You will have approximately 1 week to complete each homework assignment. These homework assignments are to be turned in by 6 p.m. on our Monday meetings for lab. There will be no exceptions to these due dates unless you have extenuating circumstances, including jury duty, military duty, court duty, or some type of required job training. Please inform me if you qualify for any of these exceptions. There will be 2 proctored exams in this course. Please make sure that you are present for these events. If you are unable to make these events, please inform me well in advance. These dates will be February 23rd at 6 p.m. That will be our midterm, and on May 4th at 6 p.m. The February 23rd meeting is actually during a lab meeting, so that should be within your schedule if you have registered for that class. Late homework will be accepted past the due date, but they will be penalized 20% off each day. And in order to hand in those assignments, you will have to scan those in and send them to my email address. Again, to reiterate, that homeworks are due at the beginning of our lab meetings on Monday. If they are turned in anytime during or after the lab meeting, it is considered 1 day late. As you see in the grade breakdown, 25% of your course grade will be accredited to your quiz score, 25% to your homework scores, 25% to your midterm, and 25% to your final. There will be a total of 8 homework assignments throughout the semester. Homeworks will be graded by myself selecting 5 questions from the homework and grading those. Make sure to complete all the questions in your homework. And start early in order to give yourself time so you can ask questions via the email or during office hours or during lab meetings. There will also be a total of 6 quizzes. The quizzes will be based off of your homework problems. So if you do your homework and understand your homework, you should do well on the quizzes. The quizzes will not be long. There will be approximately 5 to 10 multiple choice questions. The quizzes will be given on our Monday meetings at the beginning of our lab meeting, and it should take about 10 to 15 minutes. You'll find the dates of our quizzes on the course syllabus, as well as the due dates of our homework assignments. Here is our semester lesson plan. I have noted the days that the PowerPoints of each chapter should be posted, and I have also noted when our homework and quizzes are due. Note that the homeworks are generally assigned on Wednesdays, so that is when the PowerPoint should be posted by, and the homework due dates are on Mondays on our lab meeting, so our first homework is not due until January 26th. We will also have a quiz that day. As noted before, the quizzes will be administered at the beginning of each lab class, so make sure you are punctual If you are late, you will not be given additional time. You also see that the midterm is scheduled for February 23rd, as mentioned previously. The midterm will be based on chapters 1 through 5. Here is the second page of the course lesson plans for the semester. Just to note again that the final is scheduled for May 4th. It's going to be a fully comprehensive final exam, so all of the chapters will be included in that final exam. I will try to post some example questions before we have our midterm and final, so you will know what to expect on those exams. Now we will start our discussion of the first chapter, which is chemistry and measurements. Chemistry is basically the study of matter and its composition, structure, properties, and reactions. So we'll be looking at many of these topics throughout the semester and try to understand how these are all connected to each other. Before we get into many of the topics that will be discussed in this class, we will have to review some measurements and units of measurements and calculation of measurements as they will be used throughout the semester. So we use measurements every day. Especially if you are in the medical field, you will always have to use some type of volume measurement, or you have height measurements or weight measurements. And so we use lots of measurements in our everyday lives, and that also includes chemistry. Chemistry is much in the same way in that we use lots of numbers and lots of measurements in chemistry. We use a lot of math, and so we must be prepared to use math and be able to understand how and what these numbers mean. And so that's what we'll be talking about in this first chapter and first section. We use many different measuring tools in chemistry. We'll be using many of these tools in our lab classes, and we'll talk about many of these instruments when we get to lab. We also use many instruments of measurement in the medical field. You use rulers to measure height. You use scales to measure weight. And in this case, in this picture, you see this caliper measuring the thickness of the skin. So in every measurement, a number is followed by a unit. So if you are reporting a number in this course, you will 99.9% also have to include a unit. A number is basically meaningless without a unit. So as you see in this little table, we have these numbers before the unit. So make sure that when you perform calculations in this class that you are reporting a unit with your numbers, as most likely you will have to do so. The scientific community, as well as much of the medical field, uses the metric system, and as well as the international system of units. The international system of units uses metric units, but they are the base units. The convenient use of the metric system is through its use of the power of 10. And so we will discuss shortly how we can convert units and how we can use different prefixes, and they are all based on the unit of 10. Here you see a table of metric and SI units. For the measurement of length, we use the meters in the metric system as well as the SI system. For the measurement of volume, we use liters in the metric system, but because volume can be calculated by length times width times height, as many of us have learned in math classes, the SI unit is cubic meters. For the measurement of mass, we use grams in the metric system and kilograms in the SI system. Very similar, just a different power scale, and we'll talk about that in just a short bit. The measurement of time is all in seconds, and in the metric system, we use Celsius to measure temperature and Kelvin to measure temperature in the SI system. And we will talk about how we can convert Celsius to Kelvin and Kelvin to Celsius in the future slides. Here you see that we use a meter stick to measure length. The unit for measurement in the metric and SI units is the meter. In English units, we use inches, and so if we want to convert inches to meters or centimeters, we usually use this conversion. 1 inch is equal to 2.54 centimeters. And so I'm not going to ask you to memorize that value. If you need to use that calculation or that conversion on an exam or a quiz, that will be provided to you. For volume, volume is in essence just the space occupied by a substance, so just how much space does something take up. We use the liter in the metric system, and here you see the conversion. 1 liter is equal to 1.06 quarts. Again, I'm not going to ask you to memorize that. I really don't ask you to memorize information that is quickly accessible to Google. I see it as not very important to have to memorize, and I'd much rather you spend the time to understand these concepts. In the SI system, we use cubic meters, and as I said before, it's because volume is calculated in large part length times width times height, and so since those are all length measurements, the length cubed is meters cubed, and so that's where, and then that's why meters cubed is the SI unit. It's the base unit. And in this class and in lab classes, we'll be using a graduated cylinder a lot of times to measure volume. Sometimes we'll use other pieces of glassware, and we'll talk about those when we get to lab. To measure mass, mass is just is how much matter or how much material something contains. We use a balance to measure mass. The metric system uses grams, and the SI system uses kilograms. But in essence, they are all the same base unit of grams. In temperature, temperature measures how hot or cold something is. And we also say that temperature is how much energy is synonymous with how much energy something contains. In the metric system, we use the Celsius scale, and the SI system, we use the Kelvin scale. We'll talk about that conversion shortly. The time scale that we use for the metric and SI system is seconds, and so we just measure that by stop clocks and atomic clocks. Here we'll just do a quick learning check. Since these are quick and easy examples, these don't really require any calculations, but when we get to the point where we have questions that require calculations and multiple steps, what I will do is I will record videos of me solving the problem step by step and post them onto the Angel website so you can see the breakdown, how you should think about solving these problems that are very similar to what I expect you to be able to complete on your own. But here, we'll just go over these few scenarios. So we just have to match up these different units of measurement with these different measurements conducted in different scenarios. So in A bag of tomatoes is 4.5 kilograms, and if you remember, kilograms is the SI unit for mass, and so scenario A is choice 2. Scenario B, a person is 2.0 meters tall, and so if you recall, meters is the metric and SI unit for length, And so scenario B is choice 1. Scenario C, a medication contains 0.50 grams of aspirin, and so grams is the metric unit for mass, so scenario C will be choice 2. And then lastly, a bottle contains 1.5 liters of water, and so liters is the metric unit for volume, so that would be choice 3. And so here you see the answers. I will also post the PDFs for these presentations so you can kind of quiz yourself without seeing the answers on your own time. All right, so again, another learning check. So here we're going to identify the different measurements that has an SI unit. So here we want to make sure that we're using SI units, just not metric units. So just remember the slight distinction between the two. So here John's height is, so 1 is yards, 2 is in feet, and 3 is in meters. So yards and feet are both American custom units, not used in the SI or metric systems. So here would be 2.1 meters. Choice B, the race was 1 in. Choice 1 is in seconds, 2 is in minutes, and 3 is in hours. And so here, well, if you recall, both in the metric and SI systems, time was measured in seconds. Scenario C, the mass of a lemon is, and so here we have 1 is in ounces, 2 is in kilograms, 3 is in pounds. And so the SI unit for mass is kilograms, so that would be choice 2. And then lastly, scenario D, the temperature is, and so we have choice 1 is in Celsius, 2 is in Kelvin, and 3 is in Fahrenheit. And so here it's asking for SI unit, and if you recall, SI unit for temperature was Kelvin, and the metric system was degrees Celsius. So here it's going to be choice 2 since it's looking for SI units. All right, and there you see these solutions. So now we're going to discuss the topic of scientific notation. And scientific notation is used to simplify very large and very small numbers, to get rid of all those different placeholders and a lot of long numbers. So we can just simplify them into very short, concise numbers without losing any information. All right, if we look here, if we look at the width of a human hair, the width of a human hair is 0.000008 meters. That's a lot of zeros to have to write down every time you want to discuss something in this scale. So here, if we just use 8 times 10 to the minus 6 meters, then that would alleviate a lot of extra writing that we don't need to use. If we, same thing, if we look at, 4,500,000 seconds, we can shorten that up by just writing 4.5 times 10 to the 6 seconds. So we'll discuss how are these numbers written. How did you come up with 8 times 10 to the minus 6? How did you come up with 4.5 times 10 to the 6 seconds? So we'll talk about that in this lecture, and then I'll also show you, as I just mentioned earlier, an additional video of me actually writing down and showing how to go through this process of how to come up with these scientific notation numbers. But scientific notation, again, is based on the power of 10. So we'll have a number, as you saw before, we have a number, then it's times a number, a power of 10. So it's a number multiplied by some type of power of 10. So here we have the first number we call a coefficient. So we have 1.5 times 10 to the second power. All right, and so 10 to the second power, so if you square 10, you get 100. So that's what that is saying is 1.5 times 100. And so if you times 1.5 times 100, you get 150. In the second case here, you have a coefficient of 7.35 times 10 to the minus 4. So if you plug this into your calculator, it can show you that you are going to have, if you just do 10 to the minus 4, and then you multiply that by 7.35, then you will get 0.000735. So what you can make note of is that when you have a positive power and behind the 10, then you know that you should have a larger number. You will be moving your decimal place to the right, or your number will be expanding to the left. Hopefully that's not too confusing, but we'll kind of go through this a few times. And here, in the second scenario on the bottom, you see that we had 3.78 times 10 to the minus 3. So that means you're going to move your decimal place to the left, and your number will be expanding in the direction of the right. So here you see the table of powers of 10. And what you can notice here is that there's a line separating the top to the bottom for a reason, and that is because they're separating the negative from the positive exponents that are following after the 10 that you're multiplying your coefficients by. And so what you see here is that when you have 10 to the power of 1, what you're doing is you're taking 10, raising it to the power of 1, so you're just doing 10 times nothing, and so you're just multiplying your coefficient by 10. As in the case that we explained before, when we had a number that was multiplied by 10 to the second power. So 10 to the second power is 10 squared, so you're multiplying 10 by 10, and so you're multiplying a coefficient by 100. All right, and so when you are multiplying your coefficients by a power of 10 that has an exponent in the positive value, then you should be having larger numbers. In the reverse, on the bottom of this table, you see that here our exponents are in the negative values. And so these numbers will be making your coefficients smaller. And so 10 to the minus 1 is 1/10, so you're multiplying your coefficient by 1/10, or dividing it by 10. Same thing with 10 to the minus 2. All right, 10 to the minus 2 is 1/100th. So you are basically multiplying your coefficient by 1/100th, or you're dividing it by 100. And so your numbers are getting smaller. So here is just a quick comparison of, showing the differences in the standard way of writing the numbers if you wrote out every single digit, or using scientific notation. And you can see in most of these cases that they are much easier on the eye and much shorter numbers when you use scientific notation. Now, arguably, the mass of a human of 68 kilograms, or 6.8 times 10 to the 1 kilograms, that kind of seems arbitrary on why you'd make that conversion. But in the other cases, the diameter of the Earth and length of a virus, you see we have a very large and very small number with a lot of zeros in them. And so to shorten those up and to get rid of a lot of those zeros, scientific notation makes that number look a lot cleaner and hopefully easier to understand. All right, and so here we see what we're asked to do in this learning check is to select the correct scientific notation for each of these values. So if we have in part A, 0.0000008 meters, all right, we have these three different choices. And first off, should be able to easily eliminate choice 1. All right, and choice 1, it has a positive exponent, so your number should be a large number in that case, and we obviously do not, and so we should not have a positive exponent. Now, in the case of 2 and 3, what you can look for here is that our difference in coefficients. We have a coefficient of 8 and we have a coefficient of 0.8 in choice 3. One thing to note with your coefficients is that your coefficients should always be between the values of 1 and 10. So your coefficient should never be smaller than 1 and should never be larger than 10. And so we can eliminate choice 3 because that's an incorrect way of showing scientific notation. So we should select choice 2. In question B, we have 72,000 liters. And so here, again, we can look at first our different exponents, and we see that choices 1 and 2 have positive exponents, and choice 3 has a negative exponent. We have a larger number, a number that is greater than 1, so we should have a positive exponent. And so we can eliminate choice 3. Then again, in that discussion of our coefficients, in choice 1, we have a coefficient that is indeed between the values of 1 and 10. But in choice 2, we have a number that's much larger than 10. And so we should not be reporting 72 as a coefficient in scientific notation. And so we should select choice 1. Here, I just wanted to make a quick note on how we actually can come up with where that exponent comes from. All right, and so here we can come up with and just determine our exponent based on how our decimal moves. Okay, and so if we have our decimal at 0.0000008, all right, we can, as we discussed before, the correct answer for the scientific notation is 8 times 10 to the minus 8. So that negative 8, how I figure it out, is how many places did that decimal have to move over. And so here you see that our decimal started here and we had to jump over 1, 2, 3, 4, 5, 6, 7, 8 places in order to get that decimal after that 8 digit. Okay, and so and because we have a very small number, a number that's less than 1, then our exponent should be negative. So if we move our decimal in the direction to the right, then we should have a negative exponent. All right, and so it's a little bit hard to show on the PowerPoint presentation, and so as I mentioned earlier, I'll do a couple of examples in an additional video and post that to the Angel website to make it easier and to see the steps involved. All right, and so here again, the learning check, very similar, just in the opposite direction. Write each number or each of these scientific notation numbers as a standard number. And so here we have 2.0 times 10 to the minus 2. And so the first thing we can look at is that our exponent is a negative value. So that means we should have a small number, a number that's less than 1. And so first off, we can eliminate choice 1. Then we are down to choices 2 and 3. And so we have a negative exponent. And so that means we're going to move in this case, since we're going in the opposite direction, where we should move our decimal to the left, since we should have a small number, and we should move it 2 places to the left. And so we should have 0.020 seconds. Okay, and so if we move this decimal 1, 2 spots over, then we would have a placeholder in front of the 2 and following a decimal, and so we should have choice 3.02. You can also do these in your calculator, as you'll be allowed to have calculators on the exam, so which will also make it easier. Choice B, we have 1.8 times 10 to the fifth grams. Again, we have a large number, so a number that's greater than 1, so we should have a positive exponent. And so we can eliminate choice 2, because we would have a large number. And so then we're down to 1 and 3. And so here we have an exponent to the fifth. And so that means we should move our decimal 5 places to the right. And so we should end up with choice 1, 180,000 grams. And so here, just a quick check. These are the solutions. And so hopefully you're able to follow along. But again, we'll do some examples in an additional video to show how it was done. So here in this part of the chapter, we'll talk about measured numbers and significant figures. This can sometimes be a difficult topic to understand in significant figures, so we'll do our best. And again, there'll probably be some examples in that additional video of me showing how to solve some of these problems. But we use different measuring tools in order to come up with measured quantities such as height or mass. And so since we are using a tool to measure these numbers, they are called measured numbers. So when we're not using digital measurement tools, we ourselves are measuring them. And so when we are measuring these different values, maybe in this case, we're measuring length using a meter stick. We have these different lines on this meter stick representing the different lengths. And so each of these lines is spaced by 1 decimeter. And so, or we'll talk about what decimeter means, but in this case here, we see that we have 10 lines from the 2 and the 3. So that means that we have 2 and 2.1, 2.2, 2.3, so on and so forth at each of these dashes between 2 and 3. And so our blue line here goes a little bit past the 2.7, but not quite at the 2.8. And so we can try to estimate to our best ability what that number is. And so it's approximately halfway between the 0.7 and 0.8. And so we can report our value to 2.75 and 2.76. And so there is some uncertainty within that 0.5 or 0.6, or I should say 0.05 or 0.06. And so that last digit is an estimation, but it's an approximation and it's somewhat accurate, but we can still report it. So we call that 2.7, the digits of 2 and 7, as certain numbers, but that final digit was an estimation because there was no real lines to really prove or be exact with that measurement or that quantity. And so that's just an estimated value, and so there is uncertainty attributed to that. And so all 3 of these digits are called significant, including that estimated digit. And so when these values, we'll talk about, and we're going to talk about the steps of how we can determine how many significant figures are in a value, and then how many we are allowed to report in calculations. So here is another example very similar to the one we did with the blue line. And so here we're asked to measure the length of the red line. And we have this meter stick that has lines for each centimeter. And here we see we have the red line going slightly past the 9 centimeter mark, but it's not quite at the 9.1 centimeter mark. And so we can report, since we have this measuring tool measuring at each point 1 centimeter, then we're allowed to report 1 digit past that. So we can eliminate choice 1 because we can estimate that last digit or that second digit past the the decimal. And so we're a little bit past the 9 centimeter mark, and so we can report this number as approximately 9.03 or 9.04 centimeters. It's an approximate, an estimated value. They're very close in values, and so it's really hard to delineate between the two without having additional lines. And both of them can be reported, as you see in the solution. Again, we have a very similar scenario. We have another red line, and we have this red line reaching up to the 4.5 centimeter mark on the measuring tool. And so looking at that red line, it looks as if that the red line ends exactly at the 4.5 centimeter mark. And so you can use and report a 0 as that estimated digit, or that last digit that's not viewed on our meter stick. And so if it lands directly on that mark, use that 0, report that 0. So significant figures are the number of values that a measurement includes, and that includes all the known digits that are actually reported on the measuring tool, as well as the estimated digit that you come up with by looking at the tool and the measurements from that tool. And so the number of significant figures just depends on the measuring tool that you're using, and depends on how many marks are on that measuring tool, and how accurate of a measuring device you have. Here is a table of the determination of how many significant figures are in different values. And so we're going to go through each of these rules in detail in the following slides, but this is just a quick reference table that you can use and refer back to as a quick summary. So in determining how many significant figures we have, one of the first rules is that all non-zero numbers in a measured number are significant. So as long as the only confusion that really lies in determining how many significant figures comes with the zeros, because if it is a non-zero number, it is going to be significant. So in all these measured numbers, if they are in this table on the bottom, if we have 38.15, they're all non-zeros, they're all significant, they're 4 significant figures. And so if they're not zero numbers, then you can just count how many digits you have, and they're all going to be significant. And you do that in each of these examples here. 5.6 is 2 digits, 2 significant figures. 65.6 pounds, 3 digits, 3 significant figures. 122.55, it's 5 digits, 5 non-zero digits, 5 significant figures. So numbers are zeros that are between two non-zero numbers. They're sometimes called sandwich zeros, because you have the bread as our non-zeros, and then the zeros as the meat and cheese, I guess you can call it. And so those middle zeros that are sandwiched between two non-zeros are significant. And so you see that in this case, in the examples in the bottom of the table. 50.8 millimeters, that zero's in the middle, it's significant. And we have 3 digits, so it's 3 significant figures. In 2001 minutes, we have all those zeros are between two non-zero numbers, and so those are significant. So we have 4 significant figures. In the third one, the only significant zero is the one between the 7 and the 2, and we'll discuss why that is shortly. But that is the only significant digit, and so we have so we have 7, 0, and 2 as significant digits, and so we have 3 significant figures in all. And then in the last one, we have two sandwich zeros between a 4 and 5 and a 5 and a 5, and so we have 5 significant figures in that case, and that 0 before the decimal is not significant, and as mentioned before, we'll discuss these further rules. So now we will talk about trailing zeros. So trailing zeros are zeros that are followed after non-zero numbers, and there is no decimal point after those zeros. So that's key right here, is that there's no decimal point following these zeros. So if there is no decimal point, then these are not significant. And so they're just considered placeholders. They're just holding their place and making the number look large. And one way that you can remember that, and how I remember that, is if you write these numbers in scientific notation, you're not going to report these trailing zeros. They're just going to be basically cut off because they're not significant. And so in these numbers, in the measurement of 25,000 centimeters, those zeros, those trailing zeros, there's no decimal point, so those zeros are not significant. And so it's just a 2 and a 5 as significant, and so there's two significant figures. 200 kilograms, those two zeros are not significant, one significant figure. 48,600, those zeros, those two zeros, not significant, three significant figures. And then lastly, 25,005,000. So those sandwich zeros are significant, and the trailing zeros are not significant. And so the only significant values are the 25005. And so that's 5 digits, 5 significant figures. Leading zeros. So these are zeros that precede non-zero digits in a decimal number. So they come before any non-zero digit in a number that is a decimal number. And so these are not significant values either. And very similarly, if you were to write these numbers in scientific notation, you would shorthand that, and you would not have those zeros reported in the coefficient. And so they're not significant numbers. And so here, the 0.008, those zeros before that 8 are not significant. So only the 8 is significant in that value. The 0.0156, only the 1, 5, and 6 are significant. So there's 3 significant figures. The 0.00242, only the 4 and the 2 are significant, so there's 2 significant figures there. And the last one, 0.000262, only the 2, 6, and 2 are significant. Those leading zeros are not, and so there's only 3 significant figures. So determining the number of significant figures in scientific notation is much the same as any other number. You're just going to be concentrating on the coefficient. And so if you concentrate on this, just on the coefficient in these 3 different values, if we just have 8, then it's just one significant figure. If we have 8.0, that 0 after that decimal point is significant. Any 0 after a decimal point is going to be significant as long as it's following a non-zero number. And much of the same way as the third case, 8.00. Right? Those zeros are following a non-zero number after a decimal point, so they are significant. So they are 3 significant figures in that scenario. Alright, so quick learning check is determining the number of significant figures in each of these values or measurements. So 0.030. So those digits before the non-zero digit are not going to be significant. So the 0.0 in A is not significant. But that 0 after the non-zero, so the 0 after the 3, since it's after a decimal point, is significant. So in A, there are 2 significant figures. In part B, we have a sandwiched 0, and we have a 0 at the end after the 5, and because that 0 is after a non-zero digit, and it's after a decimal point, then it's considered significant. So in part B, we have 4 significant figures. In part C, we have those leading zeros again, and those zeros are in the decimal, but they are before any non-zero digit, so they are before the 8. And so all those zeros are insignificant in part C. So there's only 1 significant figure in part C. And in part D, we have that 0 after the 8, and because it is after a number, a non-zero number, and it's because it's after a decimal point, then that 0 is significant. And so part D is 3 significant figures. Another learning check: which answer contains 3 significant figures? Or answers, I should say. And so in choice 1, 0.4760, that 0 after the 6 is after a non-zero digit and after a decimal, so it is significant. So in that case, 4760 are all significant figures, so that's 4. In number 2, the 0.00476, those leading zeros are before that 4 are not significant, so only the 4, 7, and the 6 are significant. So that is going to be 3 significant figures in choice 2. And then in 3, we have 3 non-zero values in our coefficient, so that's 3 significant figures. So both 2 and 3 are have and contain 3 significant figures. B, all the zeros are significant in choice 1, we have leading zeros that are before any non-zero digit, and so those are not going to be significant. Number 1 is not the case. In choice 2, we have zeros after the non-zero digit, and that is after a decimal point. So yes, all of those zeros are significant in choice 2. And in choice 3, we have a sandwich 0. So sandwich zeros are significant, and we have a 0 after the 5. And so that's after a non-zero digit, and it's after a decimal. So those are all significant zeros in choice 3 as well. So in B, 2 and 3 are all have all significant zeros. And then in part C, the number of significant figures in 5.80 times 10 to the 2 is, so we concentrate on a coefficient of 5.80. The only thing we really look at is the 0, and the 0 is after a non-zero digit, and it's after a decimal point, so it is significant. So 5.80 are all significant numbers, and so there are 3 significant figures in C. Okay. Another one. In which set do both numbers contain the same number of significant figures? So in 1, we have 22.0 and 22.00. That 0 is in all of those cases in 1 are after the decimal, so they're all significant. So they have 3 significant figures in 22.0 and 4 significant figures in 22.00. So they do not have the same number of significant figures. In number 2, 400.0, all of those zeros are significant in 400.0, so that is 4 significant figures, all right? And that's because of that decimal point. And so if we have a 0 after the decimal, that's significant. And if we have the zeros before a decimal point and there's that decimal point there, those are going to be significant as long as they're after a non-zero digit. So there's 4 significant figures in 400.0, and then 4.00 times 10 to the 2. All of those digits are significant in 4.00. So there's 4 in 400.0, and there's 3 in 4.00. So they are not the same number of significant figures. In number 3, we have 0.000015, and so those leading zeros are insignificant. They are before any non-zero number after the decimal, so they're not significant. And then we have 150,000, but the 150,000, there is no decimal. So all of those placeholders are not going to be significant zeros. So we only have the 1 and the 5 in both cases being significant. And so choice 3 has the same number of significant figures, which is 2. All right, there it shows the same thing. So we talked about measured numbers, and now we're going to mention exact numbers. So exact numbers are, just by the name, they're exact. They are numbers that can be counted. If you have, 2 soccer balls, it's, you have just 2 soccer balls. There's not going to be 2.001 soccer balls or anything like that. They're numbers that are counted. We have, 4 boxes of pizza. Those are numbers that you count, and so they're exact numbers. Or they come from some type of defined relationship, some type of conversion. They're synonymous with each other. It's kind of like the measurement of a foot. A foot contains 12 inches. That's an exact number. It's not going to be 12.01 or anything like that. That's going to be exactly 12. And 1 meter, as we'll learn in a little bit, it contains exactly 100 centimeters. It's a quick conversion. And so there are exact numbers. There's no estimation within that number. All right, and so these are just some other examples of these exact numbers and some conversions. And I'm not going to ask you to memorize any of these U.S. system measurements and conversions, but you will have to learn how to convert some of these metric units. And so we'll get that into another part of the chapter. But the important part about these exact numbers is that these exact numbers have no effect on the number of significant figures that are allowed to be reported when performing calculations. And that's key. And so, as a quick learning check, exact numbers are obtained by, and so here we have a measuring tool, and measuring tools are not always exact, so in choice 1 is not going to be correct. And then we have counting and definition, and so both 2 and 3 are correct. We can count exact numbers. We said we have 2 soccer balls, we count 2 soccer balls, or we have some type of definition or some type of conversion. So then in B, measured numbers are obtained by, and that's just the opposite. We have measured numbers, we use a measuring tool, and that's choice 1. All right, and so here we are going to identify each of these scenarios as having exact or measured numbers. So gold melts at 1064 degrees Celsius. We're going to use something to come up with that measurement or that temperature, and so we have a measured number in that case. If we have 1 yard equal to 3 feet, that is a conversion. That is a definition, and so that's an exact number. The diameter of a red blood cell is 6 times 10 to the minus 4th centimeters, and so we come up with that number by measuring it, and so that is a measured number. There are 6 hats on the shelf. You're going to count those 6 hats, and so that is an exact number. And then if a can of soda contains 355 milliliters of soda, well, you can measure that volume. All right, and so that's a measured number, as you see in these cases. So in this part of the chapter, we're going to go over how we can determine how many significant figures we're allowed to report in our final calculations. And so answers in our calculations and our final numbers must have the correct number of significant figures we're allowed to report. And so we may end up with very large numbers that have very large number of decimal points, and so we need to be able to round off these numbers, and we need to be able to round off these numbers in the correct location, and to make sure we have the correct number of value digits in our values, and so we're not losing any information, and we're not giving too much information that's not really exact or accurate. So as many of you have learned in the past in your math classes, if you are going to, once you figure out where you're going to round off your number, where you are going to cut off that number, that first digit that's going to be, chopped off or, dropped, if that digit is 4 or less, then you're going to keep everything the same that's going to be kept in your reporting value. So in the case here, if we have to round 45.832 to 3 significant figures, all right, so we're going to want to keep the 4, 5, and the 8 place. We see that the 3, 2 is going to be dropped off, and because the first digit that's going to be dropped off is a 3, that is less than, that's 4 or less, right? It's less than 4, and so then the 8 is going to stay the same, and so we're going to be able to report 45.8. Whereas if we have the first digit that's going to be dropped or cut off is 5 or greater, then the last remaining digit has to be rounded up by 1. And so if we're going to round 2.4884 to 2 significant figures, so we're going to keep that 2 and that 4 place. All right, since we're chopping off the 884, that 8 is greater than 5. And so that means we need to report the last reported digit. We have to round it up by 1. So we're going to report it as 2.5. Sometimes we have to add in some zeros as far as reporting the correct number of significant figures. So if we calculate a complete final answer of 4, but we need to report 3 significant figures, then we need to report it as 4.00. Since those zeros are after the decimal point following a non-zero number, those are significant. So we can report that with the correct number of significant figures by adding those zeros. And you can see the rest done in other cases following that in the table. All right, and so here as a learning check, adjust the following calculated answers to give the answers within 3 significant figures. So here we have 824.75. So we're going to chop it off right at that decimal point. All right, and we're going to chop off that 7.5. And because that first digit we're chopping off is a 7, it's greater than a 5, and so then we need to round up the last remaining digit. So the 824 has to be rounded up by 1, so it's 825. So it would be 825 centimeters. All right, in part B, we have 0.112486 grams. So we're going to keep 3 significant figures, so the 112 place is going to be kept. All right, the first one that's going to be chopped off is that 4. All right, and so that 4 is less than 5, and so then the remaining numbers are going to be left alone. So it's just going to be reported as 0.112. And then lastly, part C, we have 8.2 liters. There we only have 2 significant figures, so if we want to report that as 3 significant figures, we need to add a 0. And in order to have the 0 to be in the correct spot, we need to add it after the 2. And because it's after a non-zero digit and after a decimal point, and so it would be 8.20 would be the correct number. And that's what you see here. So when we used measured numbers, we need to use the measured numbers to figure out how many significant figures we can report in our final answers, and that is done by looking at either the number of significant figures the measured numbers have, or where the decimal places lie and how many places or digits we are reporting in our measured numbers. And we'll investigate how this is. So we can separate these rules by looking at multiplication and division together, and then we're going to look at addition and subtraction in another case. So when you're doing multiplying and dividing, they follow the same rules. So when you're multiplying and dividing, we report the same number of significant figures as the measurement with the fewest significant figures. So whichever measured value that has the fewest significant figures determines how many significant figures we can have in our final answer. And we can use the rounding rules to obtain the correct number of significant figures as usual. So in the example, we have 110.5 multiplied by 0.048. So our 110.5 has 4 significant figures, and our 0.048 only has 2 significant figures. So if we were to plug that in our calculator, we get 5.304. That is too many significant figures we're allowed to report. We're only allowed to report 2, given by our 0.048. And so we have to round that off to 5.3. All right, and that is because our 0.4 is chopped off to give us the correct number of places. 0 is less than 5, and so there we would have to report. We can leave the rest of the remaining number alone. All right, and so just a quick check of understanding. All right, if we have 2.19 times 4.2. We can plug that into our calculator, and we would get an answer of 9.198. And so then we have to look at where can we round off, and how many number of significant figures are we allowed to report. So we have 2.19 times 4.12. So 2.19 has 3 significant figures. 4.2 has 2. So our final answer is only allowed to have 2 significant figures. All right, and so that will leave us with 9.1 and chopping off the 9 and the 8. And since the first digit that we're chopping off is a 9, that's greater than 5, so we have to round up. And so that would round it up to 9.2, which is choice 2. All right, similarly with division, we have 4.311, and that is being divided by 0.07. And so our answer would be 61 and a lot of decimal places. 5, 8, 5, 7, 1, 4, 3, so on and so forth. Okay, and so here we have 4.311, and that is 4 significant figures. And then we have 0.07, and so that only has 1 significant figure. And so only the actual number we're allowed to report is actually choice 3, because that is the only one that has 1 significant figure. All right, now I can understand your confusion if you got choice 2, because you had to round up, and you would think that would be the answer, but because of the number of significant figures allowed, we actually are only allowed to report 360, and that's because it has 1 significant figure, and so we have to round down, and that 0 is a non-significant 0. There's no decimal point. It's just a placeholder. All right, so that can be a little bit confusing. Then scenario C, choice C, or question C, we have 2.54, and that's multiplied by 0.0028. We divide that by the product of 0.0105 and 0.060, and we get an answer of 11.2888889, so on and so forth. So here we have to look at each value individually and look at how many significant figures they have. So 2.54, that's 3 significant figures. We have 0.0028, that is 2 significant figures. we have 0.0105, that is 3 significant figures, and 0.060, that is 2 significant figures. So we have the fewest number of significant figures reported in our measured values are 2, and so then we are allowed to report it as 11 exactly. And so remember that the number you're chopping off is 0.288889, and so since that first digit being chopped off is a 2, and which is less than 5, then we just keep the remaining numbers the same, which is 11. Okay, and so there you get the answer, and it kind of just shows you how you can enter this into a simple scientific calculator if you are unable to do your parentheses and such. So if you just took 2.54 and multiplied it by 0.0028 and divided it by those numbers, it would have gave you the correct value. Now, when we do adding and subtracting, these follow a separate set of rules, and so these are going to be determined by looking at the number of decimal places. So the number of significant figures is figured out by reporting the same number of decimal places as the measurement with the fewest number of decimal places. And so, and you use the rounding rules to adjust your answers. How I do this and how you can see it in this PowerPoint is that these numbers are lined up. And so what you can do is you can draw a line after the digit that is furthest to the left. So you can just draw a line. And so in this one, we have 25.2 plus 1.34. So the fewest number of decimal places is that 2. So you can just draw a line after that 2 all the way down, and so you can just kind of see where your number should end. Okay, and so if you have 26.54 as your answer, since you have that line after the 2, then you know your number should be chopped off after that 0.5. And so because that 4 is less than 5, you round down, or not round, you just keep the number the same, and so you have 26.5 as your final answer with 1 decimal place. And so we can just do a couple other examples right here. All right, and so we have 235.05 plus 19.6 plus 2. And so here we get an answer of, if we plug that into our calculator, we get 256.65. But here, if we draw the line after the 2 in the value of 2 measured value, then we would see that we're not allowed to report any decimals. So our final answer would be just 257. In question B, we have 58.925 minus 18.2. And so if we plug that into our calculator, we get 40.725. But if we were to figure out the correct number of significant figures, we would have to draw a line after the 18.2, so that 2. And so here we only have 1 decimal allowed to be reported, and so our final answer would be 40.7, choice 3. All right, and so there it kind of just shows you what we were kind of doing. So in the metric system, we use a lot of prefixes, and these prefixes have meaning, and they are basically to simplify numbers, so we don't have to use sometimes these scientific notations, or we can just simplify the number of digits that we can need to report. And so all of these prefixes that are used for these measurement and these units are factors of 10. And so if we have, we'll go over what these prefixes mean and what their values are synonymous with. And so here we have, in this table on the bottom, we have 1 kilometer. And so kilo means 1,000. So if we have 1 kilometer, that means we have 1,000 meters. If we have 1 kilogram, all right, kilo still means 1,000. And so if we have a kilogram, that means we have 1,000 grams. All right, so a kilometer and a kilogram is a lot larger than a meter and a gram. You need a lot of meters and you need a lot of grams in order to be equivalent with a kilometer or a kilogram. And so here are some other prefixes that we use. And so you can also see their scientific notations. And so they're one and the same. And you can also see their the symbols that they're used in the prefixes. I will say that for the purpose of this class, we probably will only use kilo in this table. We don't really use much of the other ones, but you may be familiar with tera, giga, and mega, especially when you are talking about computers and talking about hard drives and memory and such. We will use a lot of these prefixes that are smaller than 1. And so deci, centi, milli, micro, nano. We'll probably concentrate on those ones. We won't really talk too much about pico or femto. But you will be responsible to know what all of these from deci to nano, what those prefixes mean and how to be able to convert from these different prefixes. So in this learning check, we are asked to indicate the unit that matches the description. So a mass that is 1,000 times greater than 1 gram. And so 1,000 times greater, so if it's bigger, it's going to be 1 kilogram. Okay, so if we have 1,000 grams, 1,000 times greater than 1 gram is 1,000 grams, so 1,000 grams is kilogram. If we have, in number 2, we have a length that's 1/100th of a meter. So using that previous table, 1/100th is symbolized as centi. So centimeter. All right. Then we have 3, a unit of time that is 1/1000th of a second. So 1/1000th. So 1/1000th is milli. So that'll be 3 millisecond. All right. So just you'll have to remember what those prefixes mean, and that will not be provided for you on the test. You'll have to know what those are. Okay. And so there you see the answers. So in this learning check, we're going to look at these different things that we would want to measure, and we would have to select the correct units to use based on the scales and which would be most appropriate to report. So here we have a person's height. A person's height, millimeters is a small unit, so it would not be a very appropriate unit to use. Meters, if you think about a meter stick, that seems like it'd be a pretty good choice. And then kilometers in the scale of miles. So that seems like it'd be pretty large unit to use. So the most appropriate would be meters. If we're to measure a person's mass, milligrams is a very small unit, 1/1000th of a gram. Grams is also actually a pretty small unit. And so choice 3, kilograms would be the most appropriate to use. That's on the scale of pounds, so that would be the best choice. The distance between 2 cities. Cities are generally miles apart, and so millimeters would be very small to use. Meters, it would take a lot of meter sticks to go from one city to another, so that seems pretty small to use. So kilometers is on the scale of miles, so that would seem like the most appropriate unit to use. Then the width of an artery. So an artery, we wouldn't want to use kilometers, that would be a fairly large artery, so we wouldn't want to use kilometers in choice 3. Meters, again, would not be appropriate to use, especially if we're using that for our height. And so millimeters would be the most appropriate to use. All right, and there's the solution. And so what we often have to do in in science is use equalities and use these relationships and use these prefixes and go from one prefix to another, especially in terms of calculations. And so we can see here that 1 meter is the same as 100 centimeters. So it takes 100 centimeters in 1 meter. So if you look on a meter stick, you'll find 100 marks per centimeter. And it also takes 1,000 millimeters for 1 meter. So a millimeter, if you recall, is 1/1000th of a meter because it takes 1,000 millimeters to add up to 1 meter. All right, and so you can see here on a meter stick, we have 1 meter, and that has 10 decimeters. So it takes 10 decimeters to add up to 1 meter. A meter stick has 100 centimeters, so it takes 100 centimeters to add up to 1 meter. And then we have 1,000 millimeters in 1 meter stick, so it takes 1,000 millimeters to add up to 1 meter. The units of volume are largely based on the use of lengths. So here, if you look at a cube that is 10 centimeters wide, 10 centimeters with a depth, and 10 centimeters of a height, that is going to be classified as 1,000 cubic centimeters. And so 1,000 cubic centimeters is equal to 1,000 milliliters. And so that's also equivalent to 1 liter. And if you look at just 1 centimeter, so if you have a cube that's just 1 centimeter width, height, and depth, that would be 1 cubic centimeter. And so that is equivalent to 1 milliliter. In the biological field and in the medical field, you probably talk about cc's. So cc's is just another term for cubic centimeters. So 1 cubic centimeter, or 1 cc, is the same thing as 1 centimeter to the 3rd power, and that's the same thing as 1 milliliter. So they're all the same thing in that case. So 1 cc is 1 milliliter. When we measure mass, so mass are typically reported in either kilograms, grams, or milligrams. And so those are most often used. And so you just have to remember that it takes 1,000 grams to add up to 1 kilogram. It takes 1,000 milligrams to be equivalent to 1 gram. And you can go the opposite way too. 1 milligram would be 0.001 grams, 1/1000th of a gram. All right, and so in this learning check, we need to indicate the unit that completes each of the following equalities. And so 1,000 meters. So 1,000 meters, you have a lot of meters. And so it's going to be quite long. And so that would be 1 kilometer. All right, 0.001 grams, so 1/1000th of a gram. So 1/1000th is milli. So choice 1. In question C, 0.1 seconds. So we have that in the 10th place, it's 1/10th of a second. So 1/10th is deci. So that'd be choice 3. And then question D, 0.01 meters. That's in the 100th place, 1/100th of a meter. 1/100th is centi. That'd be choice 2. And there are your solutions. All right, and this learning check, complete each of the following equalities. So it's probably not going to. So in number 1, 1 kilogram. 1 kilogram. So we're going in the opposite way. We're trying to get to grams. So if you remember, we said that 1 kilo, it takes 1,000 grams to equal 1 kilogram. So it's going to be choice 3, 1,000. And then 1 millimeter is equal to, so we're going in the opposite direction. So it's going to be a millimeter is 1/1000th of a meter. So 1/1000th is selection 1, 0.001. And there again, the solution. And so in this part of the chapter, we'll be looking at conversion factors, how we go from one scale to another. And so we'll be using these different units that describe the same measured amounts. And so we can convert between metric units and metric units. We can convert between US and metric units and go from metric to US units, or we can go from US to US units. So all these are just using these different relationships and different equalities in order to figure out what we're trying to find in our final answer. One thing you want to make note of is when we are using these equalities, if we're going from a unit of two units of, or two measurements within the same system, those are going to be exact numbers. But if we are going from using equalities from two different systems, going from metric to US or US to metric systems, those are actual measured values. So they are going to have a certain number of significant figures within those equalities. So incorporate that in your calculations and your determination of your significant figures in your final answers. All right, and so here's just a table of the different equalities. I will not ask you to memorize the US equalities or the metric to US equalities, but you will have to know the metric and SI equalities on your own. So you'll be given this first and third column on your quizzes and tests if they were required, but as far as the metric and SI unit scale, you will have to know on your own and be able to use and not be able to have a table in front of you. If you notice, many of the packages and many of products that we buy in the US, there are both metric and US units. And so they basically use those equalities to explain how much are in each product that you are buying. So when we make a mathematical formula using these equalities, we call that a conversion factor, and it's basically just creating a fraction or ratio with the numerator and denominator and making it equivalent. So if we have the equality of 1 inch is equal to 2.54 centimeters, and just to kind of review, that is a measured value because it's going from one system to another. But if we were to put that into a ratio or a fraction of 1 inch over 2.54 centimeters, or just the reverse, 2.54 centimeters to 1 over 1 inch, since they are equivalent, that fraction is essentially 1, because if we need to use that in a formula, and if you have done math classes in the past, if we need to if we multiply something by 1, we get the same answer. And so, that's what we want to do when we use these conversion factors. We don't want to really change our answer. We just want to change our units. And so that's what we're using with these conversion factors. It's just basically using these equalities to change our units, but not change our, numbers into meaning something totally different. All right, and so if we were to write down these equalities and conversion factors for each of these pairs of units, you can just use the table that was in the previous slides. But if we go from liters to milliliters, all right, liters to milliliters, we have 1,000 milliliters in 1 liter. So milliliters is small. So you can put 1 liter over 1,000 milliliters, or just the opposite, 1,000 milliliters over 1 liter. They're the same thing. And that ratio is still a 1-to-1 relationship because they're equivalent. Hours and minutes. So there are 60 minutes in 1 hour. So you can put 1 hour over 60 minutes or 60 minutes over 1 hour. They are equivalent, same thing, just depending on what ratio you need. And then lastly, meters and kilometers. So if we have, if you remember, kilometers is very large, so it takes 1,000 meters to add up to a kilometer. So it'll be 1 meter, 1,000 meters over 1 kilometer, or 1 kilometer over 1,000 meters will be acceptable. All right, and so that kind of works it out for you there, breaks it down. So a conversion factor sometimes is, not a standard conversion. Sometimes have to use these things from the problem itself, and so it may be given to you. So, like in this example, the price of 1 pound of red peppers is $1.39, and so that's not a standard measurement. But that's what's given to you in the problem. So you can write it down both ways. 1 pound is equivalent to $1.39. So you can put 1 pound over $1.39 or $1.39 over 1 pound. They are both equivalent. Same thing in example 2. 1 gallon of gas is $2.25. So 1 gallon is equivalent to $2.25. And so you put 1 gallon over $2.25 or $2.25 over 1 gallon. Sometimes we use percent factors, and a lot of times you see this like in nutrition. And so here you want to have the ratio of the parts to the whole, and then you multiply it by 100. So if a food contains 18% by mass of fat, that means it says by mass. If you recall, mass is measured by grams, and so grams. If you think about 18%, all right. If we have 18%, we can work the math out in the opposite direction that's given to you in the formula on the top. So you can have 18 divided by 100. All right, so if you have 100 grams of food, that means you would have 18 grams of fat. Or similarly, if you have 100, you can put that as 18 grams of fat over 100 grams of food. All right, so if we were to plug that into our percent factor calculation, 18 grams divided by 100 grams of food times 100 would give us 18%. So that's why I kind of favor in the example, 18 grams of fat over 100 grams of food. I think that probably would work best to use rather than the second one that they discuss in the book and in this slide. But both are acceptable, but I think the first way it is written is easier and more consistent to use. All right, if you look at the percent factor in this problem, the thickness of a skin fold at the waist indicates 11% body fat. So what percent factors can be written for body fat using kilograms? So if we have 11% body fat, that's just saying that we have, if we have 100 kilograms of mass, that means we have 11 kilograms of fat. All right, and so you can write either of those ratios, 11 over 100 or 100 over 11. I think, again, that the first one that is written is the best. All right, so write the equality and conversion factors for each of the following. So if we have, I'm going to switch this up and just kind of go along with the solutions so you can kind of see. So we'll just kind of look at the solutions and follow the solutions here. So meters and centimeters, we'll convert between meters and centimeters. So the ratio you would set up would be either of these choices. Just recall that 1 meter is equivalent to 100 centimeters. So you can write it as 1 meter over 100 centimeters or 100 centimeters over 1 meter. Either would be accepted. A jewelry that contains 18% gold. So if you haven't noticed the pattern already, make the whole out of 100. All right, so the whole is just set that as 100, and then so that way the part that you're looking for is just whatever number that they give you in the percent. So 18% gold, if you have, that would be the case if you have 18 grams of gold in 100 grams of jewelry. All right, so 18 over 100 grams. Or just the opposite, 100 grams of jewelry over 18 grams of gold. Either would be accepted. Then 1 liter of gas is 95 cents. So you can either set that up as 1 liter over 95 cents or 95 cents over 1 liter. And so here we will go over, solving problems, how to go and figure out what the questions are asking and how to go through the steps of finding the correct answer. And so what you want to first look at is what are the questions giving you? What information do you get there? And then what are you trying to find? All right, so look at your units. Even if in much of this class, if you have no idea how to approach a problem, if you can follow the units along and use this problem-solving technique, you can usually get to the correct answer. All right, so if you can't remember how to use a certain formula, look at the units. Follow the units, figure out how we can get these certain units that you don't need in your final answer to cancel out, and how you can get to the ones that you need to stay. Okay, so if we have a person that has a height of 2 meters, what is that person's height in inches? Well, so here they give you meters and you're looking for inches. So we have our given unit of meters and we have a needed unit of inches. All right, and so we can use that in our problem-solving techniques. So we're just going to, again, look at, what unit is given, what is needed, and then, we can use this in our techniques later. So if an injured person loses 0.30 pints of blood, how many milliliters of blood would that be? So here, your given unit is pints. That's what they're giving you. And what you're trying to find, what's needed, is milliliters. All right, so that's what the question is. So what your information that's usually given is in the statement, and then what is needed is usually in the question. Okay, and so there you go. So when you set up your problems, you're going to write the given and needed units, and basically set up a plan and set up what needs to be crossed out and what needs to cancel out in your problem, and how you can get that to be, and how you can keep the needed unit. And you get that needed unit through some equality or conversion factor. All right, and so you may, like I said before, these conversion factors, you're just multiplying your units by 1 essentially, because you're using these equalities that mean the same exact thing. So you're not changing your answer, you're basically just changing the values with different units, but they mean the same thing. So the stepwise, what you can do is you want to state the given and needed units, and then write out our plan. Write out any equalities and conversion factors that you need to cancel out the units and to keep the needed units. And set it up with the numbers and calculate your answer. All right, so here we have how many minutes are 2.5 hours. So our given unit, again, is given to you, 2.5 hours. What you need is asking for how many minutes. So our plan is to go from hours to minutes. And we know that there's 60 minutes in 1 hour. So we set up our equation. We are given our unit, 2.5 hours, our conversion factor. So here we want our units to cancel out of hours. So in order for hours to cancel out, we need to have hours in our denominator in our conversion factor. And we want to have our needed unit in the numerator. So we're going to write 60 minutes over 1 hour. Okay, so that would ensure our hours to cancel out and our minutes to remain. And so then we can plug that into our calculators, 2.5 times 60, and we get 150 minutes. Okay, and so if we look at the last part would be the number of significant figures. So since we have 2.5 in our given unit, that is two significant figures. Our conversion factor is an exact number, so we do not get any significant figure information from there. So it's just going to be based on the measured unit of 2.5 hours. And so we have 150 minutes. So we want to make sure that our final number does not have a decimal point, and so we can keep 150 without a decimal and have two significant figures. Here, a rattlesnake is 2.44 meters long. How many centimeters is the snake? So rather than me than just explaining and not seeing the work, we'll show it here. All right, so we have a given unit of 2.44 meters, and we are asked to convert that to centimeters. And so our plan is to go from meters to centimeters. If you recall, the equality is that we have 100 centimeters in 1 meter. So our two factors that we either use is 1 meter over 100 centimeters or 100 centimeters over 1 meter. So if we look at our setup, we know that in our plan, we know we want to go from meters to centimeters. So we want our meters to cancel out. So that means in our conversion factor, that means we want our meters to be in the denominator and keep the centimeters in the numerator, our given, our needed value, our unit. So we multiply 2.44 meters times it by 100 centimeters over 1 meter. Our meters cancel out. We're left with centimeters as our unit, and we get 244 centimeters. All right, so we have three significant figures in 2.44. Our conversion factor is within the same system, so it's an exact number, and so 244 can be reported as three significant figures. Very often is the case that we need to have more than just one step, and so it's the same process. We just have to have multiple steps, so you may need to use multiple conversion factors before we can get to the correct answer. All right, so just break it down if you need to even further. What one unit, if you're still looking at what you're given, what you need, you just happen to may need a middleman. All right, so if we look at how many minutes are in 1.6 days, all right, we are given the unit of days and we need the unit of minutes. So if we come up with our plan, all right, we know days is in the beginning, we know minutes is in the end. What's the middleman? Well, it's going to be hours. We can first figure out how many hours in a day, then how many minutes are in an hour. So then we set up our problem. We know we're given 1.6 days. We want the days to cancel out. So we put 24 hours over 1 day. All right, again, in our second factor, we want our hours to cancel out. So we put 60 minutes over 1 hour. So that would make our hours cancel out. And then you just follow the math. 1.6 times 24 times 60, you get 2,300. All right, and so you can leave it as 2,300 minutes or simplify it in scientific notation as 2.3 times 10 to the third. All right, 1.6 days is a measured number, so we have two significant figures, and 24 hours in 1 day and 60 minutes in 1 hour are both exact numbers within the same system, and so we have don't have to worry about any significant figures in those cases. When you are setting this up, especially with the multiple steps, just make sure that your unit cancellation is in the setup. So just look at how you're setting it up, even without the numbers. Just look at the units and see if the correct ones are canceling out and the right ones are the needed unit is remaining. All right. So in this example, you can see what is wrong with the following steps. So if you look at 1.4 days times 1 day over 24 hours and timed by 1 hour for 60 minutes, we see there that the days are not canceling out, all right, as they would need to be. And so our units in the end would be way off and totally incorrect. And so before you even set it up with the numbers, you can just look at the units, make sure that the right things are canceling out and the right ones are staying. All right, so here we'll do another example. So what is 165 pounds in kilograms? So this is a nice simple one-step problem. So we're given 165 pounds. We need to get it to kilograms. We need to go from pounds to kilograms. There's no additional steps there. So we use the equality of 1 kilogram is equal to 2.2 pounds. And so we set up our two different ratios that we could use, 2.2 pounds over a kilogram or kilogram over 2.2 pounds. So since we know we need to go 2 kilograms, we want our kilograms, our needed unit, in the numerator. And so that would mean we would use the second conversion factor, 1 kilogram over 2.2 pounds. So we set that up, 165 pounds times 1 kilogram over 2.2 pounds, and we get 74.8 kilograms. Then we can look at the significant figures. So we have 3 significant figures in 165, and we have 3 significant figures in 2.20. And so that means, and we're doing multiplication. So that would mean that we are allowed to report the fewest number of significant figures, which is the same, which is 3. And so that leaves us with 74.8. All right, so just another quick note, because we're going from metric or from US to metric units, that is a measured value. So that does play a part in the number of significant figures allowed to be reported in the final answer. Here, a bucket contains 4.65 liters of water. How many gallons of water is that? So we're given the liters. We need to get to gallons. All right, and so if you don't have the quick conversion from liters to gallons, then you have to use the middleman of quarts. And so here our plan is going to be from liters to quarts, then from quarts to gallons. All right, and because these are going from a metric to English units, so that liter to quarts is going to be a measured value, and the quart to gallon is going to be a standard or exact value. Okay, so we go here and can see how it breaks down. And we want to just make sure that in our first step, we have 4.65 liters times 1.06 quarts per liter. So we want those liters to cancel out. So that's why we use the liters in the denominator of our conversion factor. And then we multiply by 1 gallon per 4 quarts. So that's the 4 quarts. We want the quarts to cancel out because we need the gallon to remain. And so that's why we use 1 gallon per 4 quarts. And our first measured value, 4.65, is 3 significant figures. The second is 3 significant figures because it's going from different systems. And the 1 gallon per 4 quarts is an exact number, so that does not play a part in the significant figure in the allowed to be reported in the final answer. And so our final answer has 3 significant figures, so we leave it as 1.23. All right, and so we'll do another example. If a ski pole is 3 feet in length, how long is the ski pole in millimeters? We'll work this through together. All right, so we're given 3 feet. We need to get to millimeters. So we need to go from feet to inches, then inches to centimeters, and centimeters to millimeters. So there's quite a few steps here. So we go from feet to inches. That is from US to US unit. So that's an exact number. 1 feet is 12 inches. Then we go from inches to centimeters. So in 1 inch, there's 2.54 centimeters. That is a measured value. And then we have 1 centimeter is equal to 10 millimeters. So that's an exact number. All right, so in the first step, we need to go from feet to inches. So we want to make sure our first conversion factor has feet in the denominator to cancel out, and our inches remain. Then our second conversion factor, we want inches to cancel out with centimeters remaining. So inches goes in the denominator. And then lastly, from centimeters to millimeters, we want centimeters to cancel out. So we need centimeters in the denominator and millimeters in the numerator. And then we have, then we can just do out the math. 3.0 times 12 times 2.54 times 10, and we get 910. It's a, that's a rounded number. We don't want to have a decimal point. We only want two significant figures there. Because 3.0 is two significant figures, and 2.54 is three significant figures. So we need to report the fewest number, which is 2. All right. The other two conversion factors are exact numbers, so they do not play a part in the determination of number of significant figures. All right. So when you do multiple steps like this, just double check, make sure the the math works out, make sure the units cancel out properly. Another one. If your pace on a treadmill is 65 meters per minute, how many minutes will it take for you to walk a distance of 7,500 feet? So here they're giving you the conversion factor. All right, so 65 meters per minute. All right, so that's where this one kind of plays a little bit different than the others. All right, so you're given, you want to walk 7,500 feet, and you want to you're at a pace of 65 meters per minute, and you need to get to how many minutes are you going to require. So you're going to go from feet to inches, which is a standard US conversion, 1 feet per 12 inches, then inches to centimeters, so 1 inch per 2.54 centimeters. Then you go from 1 meter to 1 meter is equivalent to 100 centimeters, which is an exact conversion. And then we were given the pace of, in 1 minute, we walk 65 meters. And we can use 1 over 65 or 65 over 1, doesn't matter. So then we have 7,500 feet. We want to make sure our feet cancel out, so we put 12 inches over 1 foot times 2.54 centimeters per 1 inch. And it seems like some stuff got disjointed here in this slide. But regardless, that 100 centimeters is supposed to have a cross slash through it. So in 1 meter, that's equivalent to 100 centimeters, and so our centimeters will cancel out. And then in 1 minute, we walk 65 meters. So our meters will cancel out, and we're left with with just the unit of minutes. Then we have here 7,500 feet. We have 2.54 centimeters per inch, and then 65 meters per minute. And so the fewest number of significant figures are 2, and so we're allowed to report two significant figures, which is 35. So very similar to using conversion factors, we can also use percent factors in a problem to figure out the answer that we're looking for. So if the thickness of the skin fold at the waist indicates 11% body fat, so 11% body fat is our given percent factor. So if you recall, that means that we have 11 kilograms of fat in 100 kilograms. So we could use grams, we could use kilograms. It doesn't really matter, but since it says that how much fat is in a person with a mass of 86 kilograms, so our answer needs to be in kilograms, so we'll just use kilograms. So just when you're using these percent factors, you can use grams over grams or kilograms over kilograms. It doesn't really matter. It's just whatever is most convenient to use. You could use milligrams over milligrams, just whatever is most convenient. So here we have we want to look at, it wants us to determine the amount of fat. And so we want the total masses to cancel out. So if a person has a total mass of 86 kilograms, we know that in 100 kilograms, it's 11%, or 11 kilograms of fat. So we want our total kilograms to cancel out and the kilograms of fat to remain. So we put the 86 times 11 over 100, and we get 9.5 kilograms. So then here, how many pounds of sugar are in 120 grams of candy if the candy is 25% by mass sugar? So one thing you can see here is there's a couple things actually. We have percent and we have a mass of 120 grams, so we want to have our percent in grams, and then we're also going to have an additional conversion factor of getting grams to pounds somehow. So here we see that we have a total mass of candy of 120 grams of candy. And so we can then do the conversion of, convert grams to pounds. And then we can go and use the conversion factor of 1 pound is equal to 454 grams. And so we want to make sure our grams cancel out. And so we put the grams on the bottom there. And then we can use our percent factor. We have sugar, pounds of sugar over pounds of candy. So, with these percents, mass percents, they don't have to always be metric. They can, any measurement of mass or weight can be used. And so here we have 25 pounds of sugar over 100 pounds of candy. So the part is the amount of sugar and the whole is the candy. And so that's why we had 25 over 100 here. And so we do our answer, we get 0.066. So we are allowed to report 2 significant figures because 120 grams is 2 significant figures. And 454 has 3. And 25% has 2. We will talk about density now. And density is just a comparison of an object's mass to its volume. So if you think about if something is dense, it has a lot of mass and a small amount of volume. If something is very non-dense, then it means it has a very small amount of mass in a large volume. So density is calculated and is by definition the mass of a substance divided by its volume. So density is equal to mass over volume. Many of the times we use the units of grams per milliliter. Sometimes we use grams per cubic centimeter. Those are the most common ones, but not the only ones. Here are just some common densities. One thing that you'll want to make note of is water. Water is at 4 degrees Celsius, a density of 1.00. All right, and so that's a key one because things that are less dense than water will float, and things that are more dense than water, they sink. All right, and so you'll commonly see those types of comparisons. Okay, and one thing you can see here, ice is less dense than water, so that is why it floats. All right, if you mix oil and water, you always see that one thing it doesn't mix, and another thing you'll see is that oil will float or rise to the top. Cork, cork is less dense than water; it floats on top of the water. All right. So here we'll just practice some calculations using density and calculate density. So it says osmium is a very dense metal. What is its density in grams per cubic centimeter if we have 50 grams of osmium with a volume of 2.22 cubic centimeters? So here we're just going to use the equation that they give us. All right, we have the given mass of 50 grams and the volume of 22.2 cubic centimeters. And so we then can just use the formula that they give us, mass over volume, 50.0 grams over 2.22 centimeters. They both have 3 significant figures, so we're allowed to report 3 significant figures. So when we plug that into our calculator, we get 22.52252 grams per cubic centimeter. But because we are only allowed to report 3 significant figures, I don't know why it says 2 in the PowerPoint, but that's incorrect. It's 3, so it's 22.5 grams per cubic centimeter. All right, so A quick guide that you can use to calculate density. You state again the given and needed units. You write down the expression, the density equation, so you can figure out what can go where in this equation. You want to, if the densities are in grams per milliliter, you want to make sure that your masses are in grams, your volumes in milliliters, and make any type of conversions that you may need to, and then plug it in and solve, and just make sure that you check the number of significant figures. Sometimes, especially for irregularly shaped objects, we use a technique called displacement to measure the volume. So what this means is just you're going to displace water. So you have a water of a known volume in this graduated cylinder. In this case, you see that it's indicated as 35.5 milliliters. And then what you can do is you can take this oddly shaped object and put it into the graduated cylinder and see how much the water rises. And so after you place that zinc into the graduated cylinder, you see the volume, new volume, as 45.0. And so that difference in the amount of volume that is risen is the volume of the object, which is 9.5 milliliters, or 9.5 cubic centimeters. We can use these volumes found from the displacement in the calculation. This is just the same as any other volume measurement. And so what you can do here is you can measure the mass of this zinc using a scale. We just measured the volume by displacement, and so then you can measure and calculate the density. And so here you see that the balance came to measure the mass of the zinc as 68.60 grams. And so we take our mass of 68.60 grams divided by 9.5 cubic centimeters. You get 7.2 grams per centimeters cubed. And so remember that we can only report two significant figures as the value or measurement with the least number of significant figures is the volume, which has only two significant figures. So here we'll just try another one out together. It says, what is the density of a metal that has a mass of 48.0 grams, and that the level of water in the graduated cylinder rose from 25 to 33 milliliters. And so first we need to, we want to write down what we're given, and then figure out what we need, and figure out where we need to go in our problem. Okay, and it gives you here a nice little picture of what's going on in this scenario. So it's given that we have 48.0 grams, and it's given that the volume of water originally is 25 milliliters, and then after we put the metal in, it is 33 milliliters. And so we're looking for the density, grams per centimeters cubed. And remember that centimeters cubed is the same as milliliter. All right, so we want the 1-to-1 ratio. So first we want to figure out the volume of the object. So it's 33.0 minus 25.0, and we get 8.0. All right, and subtraction there. So we only have to we're only allowed to report one decimal. And then 8.0 times 1 centimeter cubed of 1 milliliter, because we want the centimeters cubed, and we get 8.0 centimeters cubed. So we will know the mass, and now we calculated the volume. And so we can plug that into our density formula. And we get 48.0 grams divided by 8.0 centimeters cubed. We get 6.0 grams per centimeters cubed. And we're only allowed to report two significant figures, as 8.0 has two significant figures, which is the least amount of significant figures in our division problem. As mentioned before, we typically use water as a reference and discussion of whether or not something sinks or floats. And so we just compare these densities. And so if something is more dense or has a higher density than water, it will sink. And if something has a lower density of water, then it shall float. All right, and so here we can say in which diagram correctly represents the liquid layers in the cylinder. And so they give us the different volumes, and so whichever has the smallest volume should, they give you the densities, and whichever one has the smallest density should be on the top, and whichever one has a larger density should be on the bottom. And so here we see that the oil, vegetable oil, symbolized with the letter V, should be on top. Then water should be in the middle, and K rose syrup should be on the bottom. All right, and so then we should be able to select choice 1, as you see here. Sometimes densities can be used as a conversion factor and be used as an equality. And so you can use it either way. You can use grams over milliliters, milliliters over grams. They are synonymous with each other, just as the other ratios could be flipped, as can this. And so if we say the density of octane is a component of gasoline and has a density of 0.702 grams per milliliter, what is the mass in kilograms of a 875 milliliter volume of octane? And so we see here that we're given the density, we're given the volume, we need to figure out the mass. All right, so we're given the grams per milliliter, we need to get to kilograms. So we need to go from milliliters to grams, and go from grams to kilograms. So the density is, we can use as a conversion factor, 0.702 grams is equal to 1 milliliter. And remember that 1 kilogram is equal to 1,000 grams. So we want our milliliters to cancel out, and then we want our grams to cancel out and be left over with kilograms. So here we have 875 milliliters times 0.702 grams per milliliter. So our milliliters nicely cancel out. And then we have 1 kilogram over 1,000 grams. So our grams now can cancel out. We're left over with kilograms, and we have 0.614 kilograms. And so our 875 has 3 significant figures. It's, 0.702 has 3 significant figures, so that's the least number of significant figures reported, so we can report 3 significant figures in our final number, our final answer. So in this learning check, we will look at olive oil, and it has a density of 0.92 grams per milliliter, and it asks how many liters of olive oil are in 285 grams of oil, olive oil. So they give us the density, they give us a mass, and so we'll need to first look at how we can go from grams to milliliters, and then we can look at how many we'll go from milliliters to liters. All right, so that's going to be our process here. We're given the density, we're given the mass, so we need to go from grams to milliliters, milliliters to liters. And so we can set up our equation, 285 grams times 1 milliliter over 0.92 grams. And so we want our grams to cancel out, which does nicely. And then we have 1 times that by 1 liter per 1,000 milliliters. So our milliliters nicely cancel out. We're left with liters, and we're left with 0.31 liters. And so you see there that 0.92 has the least number of significant figures, and so we're allowed to report 2 significant figures in our final answer. We have a group of students collecting 125 empty aluminum cans. Take the recycling center. So if we have 21 cans containing 1 pound of aluminum, how many liters of aluminum, which has a density of 2.80 grams per centimeter cubed, are obtained from these cans? And we have these 3 different choices. And so we have several steps we need to go through. We need to first figure out how many pounds we have in these how many pounds of cans we have. Then we need to convert our pounds of cans to grams of cans. Then we can finally use our density of our cans to figure out the volume of cans, and then convert through the different volumes. So if we have 125 cans, first we need to figure out how many pounds of cans we have. So in 1 pound, 21 cans, we have 1 pound of cans, or cans will cancel out. Then in 1 pound, that's 454 grams. And then we have the density of aluminum, that's 2.70 grams per 1 cubic centimeter. Then in 1 cubic centimeter, there's 1 milliliter. And then in 1,000 milliliters, there's 1 liter. And so we remember that we want liters to be our needed unit, so we set up our units accordingly. And so then in all these multiplications and conversion factors, we have three significant figures in 125. We have 2 significant figures in 1 pound, 1.0 pounds per 21 cans. Then we have 454 grams per 1 pound. That's 3 significant figures. 2.70 grams per 1 cubic centimeter, that's 3 significant figures. So the least number of significant figures in these conversion factors is 2. So we'll have to report 2 significant figures, which is 1.0 liters. Which of these following samples of metals will displace the greatest volume of water? And so what we can want to do here is, if we're looking at the greatest volume displacement, we want the greatest volume for one of these metals. So we just need to go and calculate the largest volume of metal. So in this question, we are going to calculate the greatest volume of the metal sample, and that will displace the water the most. So we're going to go from grams to milliliters, or go from mass to volume. So in each of the cases, we will be multiplying the given unit of the mass by the inverse of the density, so the 1 milliliter over the value of mass in the density. So in the first one, 25 grams times 1 milliliter per 2.70 grams, we get 9.3 milliliters. The second one, we get 2.3 milliliters of gold, and the third one, we get 6.6 milliliters of lead. So the largest volume is of the aluminum, so that displaces the water the most. So choice 1 is the correct answer. And that concludes the first chapter's PowerPoint presentation. So I will be posting some problems that I will work through with video, so you can follow step by step on how to go through it, and writing it out rather than just looking at it on a PowerPoint. And your first homework is largely based on chapter 1, and we'll post chapter 2 very shortly, and you will be able to complete your at least start your homework, and come to the first lab on Monday with any questions and any concerns, and if you need any help concerning that homework assignment.